In this presentation, we will study one special type of counter that we call as ring counter. Ring counter is a typical application of shift register. We have not studied shift register yet, but we have knowledge of the counter, so we can move on with the ring counter in this presentation without having any prior knowledge of shift register or any other kind of register. The only change is the output of the last flip-flop is connected to the input of the first flip-flop. If I want to compare the ring counter with the shift register, there is only a single change. The change is this output Q3, that is the output of the last flip-flop, is connected to the input of the first flip-flop, that is flip-flop number 0. But in case of shift register, you will find that we don't have any feedback like this, but we have only Q3 as our output, and this is the only change that you will find. And it is good that you have some knowledge of the shift registers also, so that it will help you in the coming presentations. There is one important point that you have to keep in your mind is the number of state. In general, when you have a 4-bit counter, you use 4 flip-flops. We have done the same. We have a 4-bit ring counter and we have used 4 flip-flops, and when we ask you to find out the number of states, you just use 2 to the power 4, that gives you 16, and you will say we have 16 states and it will count from 0 to 15. But it is when we have a normal counter, but this is a special type of counter in which you cannot find a state like this. But in case of ring counter, the number of states is equal to the number of flip-flops used. This is a very important point, and there are chances that you will make mistake in multiple choice questions, so you have to keep this thing in your mind. The number of state is equal to number of flip-flop used. So in this case we have 4 flip-flops and thus we have 4 states. So I think it is clear. Now we will move to the circuit and we will see how the connections are made in this. You can see clock is there, and this clock is given to all the 4 flip-flops simultaneously at the same time. That's why it is a synchronous counter. And also we have used the overriding inputs. The ORI is a signal that is given to the overriding inputs of the flip-flop. I hope you know what is the overriding input. They are preset and clear. The preset PR, if 0, then the output of the flip-flop Q is equal to 1, and we know that it will set the flip-flop because Q is equal to 1. And when clear is equal to 0 or low, the Q is equal to 0. They are very important inputs and we have already used them when we have to count up to a particular value, and there is a separate presentation on this. If you go to the playlist and search it, you will find this presentation in which I have explained the preset and clear, why we call them overriding, why they are asynchronous. I have given all the answers in that presentation. There is very important point you have to remember regarding this preset and clear. Whenever preset is equal to 0 or clear is equal to 0, the output is going to be 1 and output is going to be 0 respectively, and it doesn't look for the value of the clock or D, the input. Whatever be the value of the clock or whatever be the value of the input, whether you are using the JK, TSR or D flip-flop, the output is going to be 0 or 1. That's why we call them overriding input. They are going to override your output. So we have used the preset and clear input in a certain manner that I'm going to explain you. This ORI is an active low signal. Whenever it is low like this, the clear and preset will be in action and there will be change in the circuit. For the flip-flop number 1, flip-flop number 2 and flip-flop number 3, you can see that this ORI, the overriding input, is connected to the clear. Whereas for the first flip-flop, the flip-flop number 0, it is connected to the preset. And let's say initially we have given the ORI, the active low signal. This will make the output Q1 equal to 0 because clear is low, and in the same way Q2 will also be 0 and Q3 will be 0. And you can see this ORI is connected to the preset for the first flip-flop, and when preset is low, the output is high. So Q 0 will be 1. So this is a very important thing in the ring counter. We have to get the presetted 1. This 1 I call as presetted 1 because we are getting it from the preset input, and you will find in some time that it follows a circular path to form a ring. This 1 that we have obtained now will follow a circular path to form a ring. That's why we call it as ring counter. And I'm just going to fill my table depending upon the results that we have drawn. The ORI, the overriding input, is given. It is an active low signal, and the clock is, don't care whatever be the value of clock, it is not going to change the outputs Q0, Q1, Q2 or Q3. I have already explained this thing. Q1 is 0, Q2 is 0, Q3 is 0, and as this ORI is given to the preset for the first flip-flop, we have Q0 as 1. So this is what we have in the first row. Now for the rest of the operation in this circuit, we will make this ORI high. This ORI will be high for the next operation, so that this clear and preset will not affect the output. So I will make it high. The 1 represents it is high throughout the operation, and now we will move to the clock. And as you can see, all these 4 flip-flops are negative edge triggered. These are negative edge triggered. So there will be a change in the circuit or the D flip-flop whenever we have a falling edge. So let's see what we have for the first falling edge. I will change the color for this process so that we can differentiate. For the first falling edge, you can see this 0 is acting as the input to the first flip-flop, which means that the data input D0 is equal to 0. I will first find out the input to the 4 flip-flops, then we will evaluate the output depending upon the truth table of D flip-flop. And I have just found out D0 is equal to 0. In the same way, D1 is equal to 1 because you can see Q0 is equal to 1 and they are connected. And D2 is equal to 0, D3 is equal to 0. Now we have the input to the 4 flip-flops, and we can easily find out the output because we have the falling edge and there is a change in the circuit. The flip-flop is operational, and when the input is equal to 0, we already know the output is also 0. So the output is 0 now, Q0 is 0, and when the input is 1, the output is 1. So Q1 will now become 1, and in the same way, when input is 0, output is also 0, and in the same way Q3 is 0. So we have our new outputs that you can see is 0, 1, 0, 0, and previous was 1, 0, 0, 0. So we have 0, 1, 0, 0. This is for the first falling edge. In the same way, we will do the analysis of the second falling edge quickly, and we will try to find out the input first. Here we are having 0, so D0 is 0 again. This is 0, so D1 is 0. This is 1, so D2 is 1. This is 0, so D3 is 0. We have our inputs. This brown one is the input now. This purple one is the input for the previous falling edge, and now we have the input as 0 for the first flip-flop. So again the output will be 0, and the output is 0 for the second flip-flop also, flip-flop number 1, because input is 0. And now the output of the flip-flop number 3, that is flip-flop 2, is 1 because input is 1, and the output of last flip-flop is 0. So we have 0, 0, 1, 0. So we have 0, 0, 1, 0. In the same way, if you do the analysis for this third falling edge, you will find the output as 0, 0, 0, 1, and again 1, 0, 0, 0. Now let's see what is happening in this table. We have to see the 1. I will shade down the 1, and then I will tell you how it is moving. You can see we have the presetted one. This 1 is presetted 1 because we got it from the preset input, and for the first falling edge it has traveled here, then again here, then here, and then here, and you can see that it is making a ring. That's why we call it as the ring counter. You will have a better feeling when you understand it by using the waveform. So we are going to draw the waveform for it, and this is the last part of this presentation. This one is the clock, and ORI is the overriding input. I have made the overriding input low initially, that I have already explained, and after that I have made the ORI high throughout. You can compare it in this table. It is a low initially, and then we have it as 1. So I have represented the same thing in the waveform, and now we will find out Q0. And initially you can see when the ORI is low, the Q0 is 1 because of the preset input. So the Q0, as soon as the ORI hits, the Q0 will go high, and it will remain high till the falling edge. We have to do the change for every falling edge. Okay, and it is high initially, and then it will go low. Okay, and if I talk about Q1, then it was high initially, and because of this ORI, the clear is low, and Q1 will go low till the first falling edge. Now this one, the presetted one, is traveled, and Q1 is high. So we have Q1 as 1, and now we will draw Q2 and Q3. Q2 was high, and then it will also go low because of the clear input, and it will remain low. In the same way, Q3 was high, but because of clear input, it will also go low. Now we will analyze the second falling edge. For the second falling edge, you can see Q0 is low. So I will make it low. You can see Q0 is low, and also Q1 will go low. It was high, but now it will go low, and Q2 will go high. You can compare it from the table. Q2 is now high, and Q3 is still low. Okay, and for the third falling edge, Q0 is low, Q1 is also low, and Q2 will also go low, and now we have Q3 as high. And finally we will analyze for this falling edge, and you will find that Q0 is high again. From here you can see Q0 is high again, and rest of the outputs Q1, Q2 and Q3 is low. Now we will see how our 1 is traveling quickly. This is 1, 1, 1, 1 and 1. You can see it is making a ring. We are starting from Q0. Remember this thing. We are now on Q1, then Q2, then Q3 and back to Q0. So we are starting from Q0, going to Q1, then Q2, Q3 and again Q0. So it is making a ring, and this one is the presetted one. It's very simple topic to understand, and it's very important at the same time. These waveforms clearly show that the presetted one shifts 1 bit per clock cycle and forms a ring. Hence the name is ring counter. And if you talk about the application of the ring counter, then ring counters are used in those applications in which several operations are to be sequentially controlled. We have to control sequentially the several operations. We have to use the ring counter. For example, in resistance welding, the operations called squeeze, hold, weld and off are to be performed sequentially. So we can use it there. If you want a separate presentation on the application of the ring counter, you can comment in the comment section. I will try to make one. And I think this is over now. We have completed the ring counter, and it will be a very important topic for you in the exam. So please practice it well. This is all for this presentation. In the next presentation, we will discuss Johnson ring counter.